Let's understand the complete machine learning process, from collecting data all the way to making predictions on completely new data. Let's first understand the basic idea behind machine learning. How does a machine actually learn? Think about how a child learns to recognize a cat. We don't teach the child a complex definition. Instead, we show many pictures and simply say this is a cat. After seeing enough examples, the child begins to recognize the common pattern. So when they see a new cat they have never seen before, they can still identify it correctly. A machine learns in a similar way. Instead of showing pictures to a child, we provide many examples to a machine learning algorithm. The algorithm studies these examples, discovers the underlying pattern, and creates a trained model. Once trained, the model can recognize or predict outcomes for new data it has never seen before. Let's look at the complete learning process. Don't worry if some of these steps seems new. We will understand each one in detail throughout this episode. It all begins with data. We provide the machine with many past examples. In this case, we have information like the area, number of bedrooms, and the corresponding house prices. Next, we choose a machine learning algorithm. The algorithm studies the data and tries to discover the relationship between the inputs and the correct answers. After learning from the data, it creates a trained model. Think of the trained model as the knowledge or mathematical rule that the machine has learned. Once the model is ready, we give it a new data that it has never seen before. For example, a house with an area of 1600 square feet and 3 bedrooms. Finally, the trained model uses what it has learned to make the prediction. In this example, it predicts the house price. Now that we have seen the overall process, let's understand what machine learning actually is. Machine learning is a branch of artificial intelligence that enables computers to learn patterns from data instead of following a fixed set of rules written by a programmer. The more relevant data the machine learns from, the better it becomes at recognizing patterns and making predictions. In fact, one of the biggest reasons artificial intelligence has advanced so rapidly in recent years is because of machine learning. Let's understand each step in machine learning in detail. The first step in machine learning is data collection. Before a machine can learn anything, it first needs data. Just like students learn from books and experience, machines learn from data. Data can come from many different sources. It may be stored in databases, collected from files and documents, retrieved through websites, generated by sensors, or entered directly by users. The most important thing is that the data should be relevant, reliable, and representative of the problem we want to solve. Data can also be structured like tables in a database or unstructured like images, emails, videos, and audio. For example, if we want to build a spam email detection system, we first collect thousands of emails from users. These emails become the data that the machine will later learn from. Why data is so important? Machine learning is only as good as the data it learns from. Data is the fuel of machine learning. The more relevant and high quality data we provide, the better the model learns and the more accurate its predictions become. Think of a student preparing for an exam. A student who practices more questions usually performs better. Similarly, a machine learning model learns better when it's trained on more quality data. It's not just about quantity of data, but also its quality. The data should be accurate, relevant, and diverse. That's why companies like Google, Amazon, and Netflix invest heavily in collecting and managing quality data. In short, better data leads to better learning, and better learning leads to better predictions. Garbage in, garbage out. Once we have collected the data, the next step is data preparation. In the real world, raw data is rarely perfect. It often contains missing values, duplicate records, incorrect entries, and inconsistent formats. Before the machine can learn, we need to clean and prepare this data. This includes handling missing values, removing duplicates, correcting errors, converting data into the right format, scaling numerical values when needed, and encoding categorical data into numbers. Think of it like washing and cutting vegetables before cooking. The better the preparation, the better the final result. Clean data leads to better learning, faster training, and more accurate predictions. Now comes the most important step in the machine learning process, training. This is where the actual learning happens. We feed the clean and prepared data into machine learning algorithm. During training, we provide the algorithm with two types of information. The first is the input data called features. Features are the characteristics or attributes used to make prediction. The second is the correct answer called label. The label is the output that we want the machine to learn to predict. The algorithm studies thousands or even millions of examples containing both the features and their corresponding labels. Its goal is to discover the underlying pattern or mathematical relationship between them. It doesn't simply memorize the answers. Instead, it learns a general rule that can be applied to a new data it has never seen before. During training, the algorithm repeatedly makes predictions, compares them with the correct labels, measures the error, and gradually improves its internal mathematical model until the error becomes as small as possible. The result of this process is trained model that can make predictions on new unseen data. At this stage, don't worry about the different types of machine learning or the algorithms involved. In this episode, our goal is to understand the overall machine learning workflow. In the upcoming episodes, we'll deep dive into supervised and unsupervised learning and then explore popular machine learning algorithms to understand how they actually learn. Once the training process is complete, the algorithm produces a trained model. But what exactly is a model? A model is simply the knowledge the algorithm has learned from the training data. It contains the patterns and relationships that the algorithm discovered during training. You can think of the model as a set of mathematical rules that the machine has learned, not the training data itself. During training, the algorithm learns from the data. Once training is complete, the training data is no longer needed to make predictions. Instead, the trained model is used. For example, if we are building a spam email detector, the model learns which patterns are commonly found in spam emails and which are found in genuine emails. When a completely new email arrives, the model uses those learned patterns to decide whether it's a spam or not spam. Once the model has been trained, it's ready for the next step, prediction, also known as inference. At this stage, we provide the model with new unseen data. The trained model applies the patterns and relationships it learned during training to make prediction. Notice that no learning happens during this stage. The model does not update itself or learn anything new. It simply uses its existing knowledge to produce the best possible output. For example, suppose a new email arrives, the trained model analyzes the email using the patterns it learned during training and predicts whether the email is spam or not spam. The final step in machine learning process is evaluation. Building a model is not enough. We also need to check how well it performs. During evaluation, we test the trained model using new data that it has never seen before. We compare the model's prediction with the actual correct answer to measure its performance. Based on these results, we calculate evaluation metrics such as accuracy, precision, recall, and F1 score. These metrics help us understand how reliable and effective the model is. You don't need to worry about these metrics right now. We'll study each of them in detail in later episodes. If the model doesn't perform well, we may collect more data, improve the quality of the data, choose a different algorithm, or retrain the model. The goal is not to build a model that only remembers the training data, but one that can make accurate predictions on completely new, unseen data. Let's understand how the machines are trained using an example of predicting student marks. So our goal is to build a model that can predict a student's marks based on the number of hours they study. To solve any machine learning problem, the first step is choosing the right algorithm. Different algorithms are designed for different types of problems. We are going to study all these algorithms in next episode. In our example, the output is numerical value, the student's marks. Since we want to predict a continuous number, the most suitable algorithm is linear regression. Our feature or input is study hours and our label or correct answer is marks. Now that we have selected the algorithm, it's time to start learning. We provide the algorithm with the training data. Each training example contains two parts, the feature, which is number of study hours, and the label, which is students' actual marks. At this stage, the algorithm doesn't know any formula or rule. It simply looks at these examples and starts searching for a relationship between the input and the correct output. Its goal is to answer a simple question: how are study hours related to marks? The next step is discovering the rule or the pattern. It starts asking questions like, if study hours increase, do marks also increase? Is the relationship roughly a straight line? By how much do the marks increase for every extra hour of study? The algorithm keeps analyzing the examples until it finds the mathematical rule that best fits the data. Remember, at this stage, the algorithm is not memorizing the marks of each student. Instead, it is learning a general pattern that explains the relationship between study hours and the marks. Now that the algorithm has found an initial rule, it's time to test it. It takes one example from the training data and uses its current rule to make a prediction. For students who studied 2 hours, the actual marks are 30. Suppose the algorithm's initial equation predicts 45 marks instead. Clearly, the prediction is wrong. This is completely normal because the algorithm starts with a rough estimate. It hasn't learned the best rule yet. The purpose of this step is simply to see how close the current prediction is to the correct answer. In the next step, the algorithm will measure the error and use it to improve its rule. The algorithm has made its first prediction. Now it needs to find out how accurate that prediction is. It compares the predicted marks with the actual marks from the training data. In our example, the actual marks are 30, but the algorithm predicted 45. The difference between these two values is called the error. In this case, the error is 15 marks. This error tells the algorithm how far its current mathematical rule is from the correct answer. A large error means the rule needs significant improvement, while a smaller error means the algorithm is moving in the right direction. But simply measuring the error isn't enough. The algorithm must now use this error to improve its mathematical rule. Now the algorithm knows that its prediction is not correct, but instead of giving up, it learns from its mistake. The error acts like a feedback. It tells the algorithm whether its prediction is too high or too low and by how much. Using this information, the algorithm adjusts the values in its mathematical equation. In linear regression, these values are called the parameters, the slope and the intercept. In our example, the current rule predicts 45 marks for a student who studied 2 hours, but the actual marks are 30. Since the prediction is too high, the algorithm modifies the equation to reduce the error. So the new rule is predicted marks equal to 15 into study hours plus 10. Now we predict again for 2 study hours and we get 40. The prediction is still not perfect, but it's much closer to the correct answer. The error has reduced from 15 marks to 10 marks. This is exactly how machine learns: predicts, measures the error, update the rule, and make a better prediction. In next step, this process will be repeated again and again until the error becomes very small. At this point, the algorithm has improved its mathematical rule once, but one update is usually not enough. This cycle, predict, measure the error, update the rule, is repeated over multiple iterations. Let's look at our example. In the first iteration, the prediction was 45, while the actual marks were 30, so the error was 15. After updating the rule, the second prediction became 40, reducing the error to 10. The algorithm improved the rule once again, and in the third iteration, the prediction became 30, exactly matching the actual marks. The error is 0 now. Since the error is no longer improving and is already small enough, the training process stops. The graph clearly shows how the error decreases with each iteration until it reaches 0. This repeating process is the heart of machine learning. The algorithm keeps learning from its mistake until it finds the best mathematical rule that fits the training data. After repeating the learning process many times, the algorithm finds the best mathematical rule that fits the training data. The final rule is called the trained model. In our example, the trained model is predicted marks equal to 10 into study hours plus 10. Here 10 is the slope, which means every additional hour of study increases the predicted marks by about 10. And 10 is the intercept, which is the model's starting value when the study hours are 0. Now let's test this trained model on all the training examples. For every study hour value, the predicted marks exactly match the actual marks. As you can see, the error for every training example is 0. The graph also shows that the prediction line passes through all the training data points, which means the model has successfully learned the relationship between study hours and marks. At this stage, the training is complete. The model has learned the pattern from the training data and is now ready to make predictions on new unseen data. Now that our model has finished learning, it's time to use it for its real purpose, making predictions on new data. This stage is called inference. During inference, the model does not learn anything new. It simply applies the mathematical rule it learned during training. Suppose we have a new student who studies 7 hours. Notice that this student was not part of the training data. The model has never seen this example before. We apply our trained model, predicted marks equal to 10 into study hours plus 10, and we get 80. So the model predicts that this student will score 80 marks. Since this is a new student, we don't know the actual marks yet. We only have the model's prediction. This is how machine learning models are used in the real world. After learning from historical data, they can make predictions for new unseen data. Thank you.